In the first solenoid example problem, we are given a solenoid has a length of 10 centimeters and in total 100 loops. So that means there are 100 wrappings of wire down the length of that cylinder. Okay, so there will be a magnetic field pointed down the central axis of the cylinder. So there will be a magnetic field pointing in this direction. And the question is, how strong is that magnetic field? So we're told that there is a current of 0.5 amp flowing through the wires that make up that solenoid. I could say then that little n is the number of wires per meter, the number of wires per unit length. In SI, the unit length is 1 meter. So I have 100 loops of wire in 0.1 meter total. So that would be 1,000 loops per meter. Loops of wire per meter. Now, when I try to find the magnetic field inside the solenoid, I would get magnetic field is mu naught times little n times I. So the magnetic field is going to be 4 pi times 10 to the negative 7, the magnetism constant mu naught. Then I have times little n, which is 1,000, times the current flowing through the solenoid, which is 0.5. I put all those numbers into a calculator, and I get the magnetic field inside the solenoid is going to be 6.28 times 10 to the negative 4 Tesla. In the next example problem with the solenoid, what we're doing is we will have a solenoid and we're going to have a particle that is moving inside the solenoid, but the particle is not moving down the central axis. The particle is kind of angled relative to the central axis of the solenoid. So in this problem, we have a solenoid that is 275 loops wrapped in over a total length of 21.5 centimeters. So we have 275 loops over 21.5 centimeters, which I'll just right now convert to meters, so that's 0.215 meter. And so what does this picture look like? We have our solenoid. And inside the solenoid, there is going to be a magnetic field. So here are the terms of my solenoid that are wrapped around. And there is a magnetic field pointing down the central axis of the solenoid. For the context of this problem, it doesn't really matter if I choose the magnetic field flowing to the left or to the right. It just means the current is either going one way or the other way. It doesn't really change anything about this problem. So in total, we have 275 loops in 21.5 centimeter. Now the particle, as we said, is moving with a certain velocity, and that particle is not down the central axis. The particle is angled. So the velocity vector of this particle would actually be angled. So the velocity vector of this particle is going to look something like this, where this angle right here is given as 11.5 degrees. So I'm going to just erase this so I have some room. I will call this angle theta. And so I could say here, the speed of the particle is 1050 meter per second, and the angle between the direction of the magnetic field and the direction of the particle's motion is going to be 11.5 centimeter. 11.5 degree. We're also given the charge of the particle is 12 microcoulomb. So 12 microcoulomb, which is 12 times 10 to the minus 6 coulomb. So the first question is, what is the strength of the magnetic field in the solenoid? We are also told that the solenoid carries a current of 2.95 amp. So from here, I have enough information to find the strength of the magnetic field. I could say B is equal to mu naught times big N over L times I. Little n is equal to big N over L. It doesn't matter which I use, whatever is convenient. So I could say the strength of the magnetic field inside the solenoid, 4 pi times 10 to the minus 7. Big N is, in this problem, 275. Little n is going to be 0.215. And then the current flowing through the solenoid is 2.95 amp. Now I put all those numbers into a calculator. When I hit enter, I get the strength of the magnetic field inside the solenoid is going to be 4.74 times 10 to the negative 3 Tesla. So we found the strength of the magnetic field inside the solenoid. The magnetic field is 4.74 times 10 to the minus 3 Tesla. Part 2 of this problem asks us to find the force on the charged particle. This particle is moving in a background magnetic field. In this context, the background magnetic field is created by the solenoid. So this problem is going to be similar to the slide from previously, where we said if you combine circular motion with motion in a straight line, you get a helical path. So a particle will move around and around in a circle, but forward, forming a helix. This is going to be that type of motion. So I could say the force on the particle is going to be given by F is equal to QVB sine theta. Now, Q is the charge of the particle, V and B we have over there. The theta is the angle between the direction of the magnetic field and the direction of the particle's velocity, or which is also going the same as saying the angle between magnetic field and direction of motion. So the angle between the magnetic field and the direction of motion is pretty small, only 11.5 degrees. So I could say the force on this particle is going to be 12 times 10 to the minus 6 times the speed of the particle, we have a 1050, times the strength of the magnetic field, 4.74, times 10 to the negative 3, times the sine of 11.5. Now if I plug all these numbers into a calculator, I get the force on the charged particle is 1.19 times 10 to the negative 5 newtons.